Hi, my name is Keim and I want to present you our work where we recover tracelinks in software architecture documentation between informal natural language text and formal models. When we have models for the architecture of a system on one hand and the documentation of architecture on the other hand, it is often not clear how to map information between these artifacts. Such links are important because, for example, the documentation may contain additional information like reasoning about a component or other information that cannot be displayed with the model. However, linking different artifacts is not trivial. Often, slightly inconsistent naming or other characteristics like using co-references render simple approaches like text search useless. The problem that we face here is closely related to classical Tracelink recovery for requirements to code. However, there are differences in available information. Code, for example, has often comments and method bodies, which models usually don't. Therefore, there's generally less information on the model side. However, there are clearer and more explicit references because there are usually names in the documentation and there's usually more similar naming between the artifacts. So to sum this up, our goal is to analyze both informal textual software architecture documentation and formal architecture models to recover tracelinks that exist between them. When looking at existing approaches in this area, most tracelink recovery approaches connect requirements to code. There are two main directions that we have here. We have on one hand information retrieval-based approaches, and we have approaches that are based on natural language processing, including machine learning approaches. Information retrieval approaches are more historically used, and one example for such an information retrieval approach is the approach by Rodriguez and Carver that are using the non-dominated sorting genetic algorithm. When looking at information retrieval approaches in general, they have different problems. For example, they usually cannot deal with polysemy and they disregard semantics. When looking at natural language-based approaches, there are a more recent trend and often also using machine learning. Examples for these include the work by Zhang, where they are using synonyms and verb object phrases, the work by Guo. They are using word embeddings and recurrent neural networks, and more recently the work by Moran that are using Bayesian hierarchical networks. One big problem of such approaches and other machine learning approaches are their reliance on training data. And often there's a lack of enough training data to properly map or to use them to their best. Coming back to our approach, our goal is to recover tracelinks between textual information, informal software architecture documentation, and formal models. Therefore, our research question is how accurately we can do that with our approach. Our contributions are that we have an extendable framework that we call Swatter for creating such tracelinks. We created a dataset for the evaluation. We re-implemented baseline approaches to be able to compare our approaches to other approaches, and we made all of these publicly available online. For our approach, we created a simple tracelink. In there, we have tracelinks that consist of a reference to the model element and to a text element. A text element is a concept in the text that consists of mentions. And mentions can either be a name or a type and might appear at multiple positions in the text. To make things more clear, mentions are an appearance or part of a textual element that should be mapped to a model element and may contain references to named elements for names and types in text. With that tracelink model in mind, let's look at the overview of our approach. First, on the model side, we extract and create model elements. On the text side, we analyze the text to identify mentions and do initial clustering of same or similar entities. We then refine and further analyze these mentions and cluster them to combine them to create text elements. Lastly, we filter and refine even more and then analyze the existing information to create finally the tracelinks. Within each step, we have modules, and these modules are responsible for identifying and initializing different analysis, for loading configuration and all the options that we have, and running set analysis and collect the results. All our analysis are agents, which means they can be dynamically loaded, and they find and the agents can find, annotate, and update results, including their confidences for their results. As a consequence, our design leads to a modular, extendable, and exchangeable framework. Within our framework, we have a main principle, which is to expand promising results, but never to discard viable solutions too early. With this main principle, we want to achieve a high recall. We and others in literature see recall more important than precision for tracelink recovery, mostly because with a high recall, it's easier to disregard imprecise and wrong tracelinks in comparison to finding the missing tracelinks. Let's look now into some more details of each processing step. At first, we retrieve information from models about elements and instances and the types of said elements. We then transform the information into our model along with storing additional information like a list of available types. Here, adapters shall provide access to the needed information, therefore adding other kinds of models or meta-models is easy. For processing the text side, we start with a pre-processing with natural language processing that includes part of speech tagging, sentence splitting, lemmatizing, dependency parsing, and much more. We then identify mentions and which words are terms that denote potential named elements or types. We use different analysis with different heuristics. For example, we look at nouns and whether they are in plural, incoming or outcome dependencies, and so on. We also look for certain patterns, for example, articles that are followed by one or more nouns. We also look for compound terms and separators. All these contribute and add to the confidence that something is a mention, and either whether something is a named type, a named element, or a type. The clustering of similar terms that we use is currently based on word similarity, which means in our case string similarity. Here, we also in the future want to experiment with other similarity measures, but right now we experienced quite good results with string similarity already. Next, we refine the existing information. Here, we combine the information about types from the meta model with information from text. This is independent from the actual model and only dependent on meta model. This way, we want to reduce potential early bias from model elements and want to focus on type information, etc. Here, we combine identified mentions that are named elements and types where possible. This way, we can potentially tell for a text element which type it should have based on the text. Let's look at the following example. We have this sentence and we identified database as mention that denotes a name and component as a mention for a type. Especially because we have the information from the meta model that there are components, we can also say with the help from our heuristic that both should be combined to a text element, especially because they are within the same phrase. Lastly, we combine all previously extracted information and we link the text elements and model elements. Here we use different heuristics again. For example, we compare the terms of underlying mentions or we compare type information, etc. As a consequence, we create tracelinks and calculate an overall confidence for each tracelink based on the used heuristics and confidence of the used information. To see if our approach can successfully recover tracelinks, we used 3 case studies in our evaluation. First, we have MediaStore, a Java EE-based case study representing a fictional digital store to buy and download music. Next, there's TStore, a microservice reference application representing a web store for T, and Teammates, a platform for managing peer evaluations and other feedbacks for students. All these case studies have different sizes and characteristics, for example, the density of Tracelinks in sentences. Here, Teammates has, for example, extensive documentation, but also a lot of sentences without any Tracelinks. On the other end is MediaStore with the least sentences, but 2/3 of these sentences contain at least one Tracelink. To quantify our results, we use the metrics precision, recall, and F1 score. Overall, we see recall more important than precision, as mentioned earlier, because this is mainly, it's easier to discard wrongly found tracelinks in comparison to finding new tracelinks. We use the classification of Hayes to assess the quality of our approach. We also compare our approach with re-implementation of two other approaches that I also mentioned earlier. First, the approach by Rodriguez and Carver that uses genetic algorithms, and the approach by Zhang and colleagues that make use of synonyms and verb object phrases in both artifacts. We choose these approaches because they are promising recent approaches that can be adapted quite easily for using models instead of code. For our result, let's first look at the MediaStore case study. Here, the results are acceptable, but the approach of Zhang is comparably precise here. These also are the worst results of our approach. For the other two case studies, TStore and Teammates, the results can be classified as excellent, and the other approaches seem to have difficulties here. Maybe this can be a sign that our approach is more resilient, but we have to explore this further. We also calculated two average scores. We have the plain average, that is the average over the project. This depicts the expected outcome per project. We also calculated a weighted average. The weight here is means that we weight the results of the projects over the number of tracelinks. This depicts the expected outcome per tracelink. Here we can also say that we have very good to excellent results on both average scores. Overall, our recall is also higher than our precision following our paradigms. We also looked into the wrong tracelinks to identify our weaknesses. One problem was that we sometimes wrongly identify terms when the terms have close naming to actual model elements. Moreover, we had some issues with model elements having similar naming. And lastly, when terms were short or abbreviations were used, the approach had some issues. After all, we employ some analysis that are based on text similarities, and sometimes this can cause these problems. This also means that if your project has such properties, you should configure parts of our approach to require, for example, a higher similarity. This leads us to our discussion and conclusion. Our results are good to excellent and outperform other baseline approaches. The biggest limitation right now is the reliance on word similarity, and we currently base this on the assumption that naming should be consistent. But this is not always the case, and other problems might come up if we just use this string comparison. This is one of the things that we also want to improve in the future work. Moreover, we want to take relations more into account. This might help us in identifying further tracelinks, and we can also even link relations themselves. Another idea is to combine our approach with other approaches to try to get the best of different worlds, so to say. Lastly, with found tracelinks or the lack thereof, we also might be able to find some inconsistencies between text and model. Here, we want to explore if we can, for example, identify when a component is described in the text but missing in the model, for example, like a cache. This might indicate that either the component was forgotten to be modeled or the text is outdated. This is the end of my presentation. Thank you all for your attention, and I'm excited to answer questions and discuss the approach with you.